Understanding variation. This is a very important concept. If you understand this well, the rest of the concepts about process capability and statistical process control will make a lot of sense. So we're going to understand it the way Deming used to teach it. And he used to teach it with this experiential exercise. So we're going to do it by imagining that we're actually doing it. And so this was the famous Deming's funnel experiment. You have a paper, and on top of the paper, held by some sort of stand or metallic arm, is held a funnel. And you have to drop marbles through the funnel onto the paper. In the exact center of the paper, you have a mark, like a dot or an X, which is the target. The goal is to make the marbles land on the target or as close to the target as possible. And obviously, at the very start of the experiment, the funnel is set to be exactly above the target, right? So you can look from the top through the funnel, and you kind of move the funnel until it's kind of above the target, and then that's where you try to fix it with some arm or some attachment. Okay. Now we want to have a way to mark the position of where the balls fall. In those days, there was what was called carbon copy paper. And you may have to Google it to figure out what it is. I'll try to describe it. But if you haven't seen it, I don't know how much you can understand. Basically, before printers got common, if you went to a shop, you bought something, or in other areas of business, things were done by hand. So you might write the receipt or the invoice by hand. And obviously, if you are giving the invoice to a customer, okay, you bought this, you want to keep one copy for your records that you sold this at this price on this date to this customer. And so if you have to write it by hand, you'd have to make 2 copies of the document. You have to write the whole thing twice and then have the customer sign both copies or something like that, right? So to make that process easier, what they would do was they would take 2 pieces of paper, and between them they would put this blue or black sheet called carbon copy paper, and then they would put these 2 sheets of paper together with the carbon copy paper sandwiched between them. And then when you would write on one side of this paper, the pressure from the ballpoint pen would push into the carbon copy paper, and the carbon copy paper would leave marks on the paper on the other side at the bottom level. So by just writing once on the top level paper, you would create a copy on the bottom level paper, and the copy gets created because the carbon copy paper, when you exert pressure on it, it leaves a mark. And if you just touch it softly, there's no mark, but if you put pressure on it, it leaves a mark. It's covered with ink or something like that, some powdered ink or whatever. Okay, so that's what they would do. They would take 2 sheets of paper, put carbon copy paper in the middle, and when the marble falls on the upper sheet of paper, it pushes on the upper sheet, pushes on the carbon copy, and the carbon copy leaves a mark on the bottom sheet. So after you've dropped a bunch of marbles, you can take out the bottom sheet and look at your pattern on where the marbles hit. Kind of like if you go to a firing range and you shoot at a target, right? The bullets make marks, and then later on you can see the marks, especially if you're doing a long distance, long range shooting, you can then see where the bullet hits versus the target. Same thing with archery, you shoot arrows and you can see the arrows make a mark, and you can see where the marks are with respect to the target. Same idea, the marbles, you're shooting the marbles down the funnel, trying to hit the target. With some technology, a mark is left where the ball falls. And you can then take out that and examine the pattern with respect to the target. That's the experiment, okay? Now, in these days, if you don't have carbon copy paper, you may use a pressure pad type of instrument which records the position wherever it's hit. Okay, kind of like same technology as a touch screen, but you don't need a touch screen. You just need like a pressure pad, which can somehow record where things hit on a computer. And it could, if you connect it to a computer, it would display on a computer screen where the things are hitting it. And so you could still do it. Or you could just get carbon copy paper, I guess, if it's still produced. Okay. And now, in Deming's case, he would give this experiment to multiple teams and tell them whichever team got the hit had marbles fall nearest to the target, so the tightest cluster around the target or on the target is going to win. And so you have to do that. And what would happen is when people would drop the marble would not always fall on the target. And so they, after every marble is sent through it, they're allowed to adjust the things up. So they can move the funnel, right? Or if the funnel is kind of locked in place, you can move the paper underneath the funnel, right? That's the same thing, because you want to move funnel relative to the target. Whether you move the funnel or the paper is the same thing in effect, whichever is easier, right? So you can adjust. That's your adjustment or tuning. So so teams would throw some marbles, examine what's happening, do some adjustment, throw some more marbles, and after 100 marble throws or whatever, then that's the results you got. Okay, you compare it to other teams. Now there are multiple strategies you can follow to try to win this game. The first strategy is what I like to call the lazy boy strategy, which is do nothing. Just set up initially, obviously, you look through it, you set up the funnel on top of the target, you connect it and you lock it in place and just drop all your 100 marbles and you're done. Like the first team to get done, do nothing, just drop the marbles. No other adjustment or tuning is done by this team. Okay. And the comparison to real life is in production systems. Sometimes, you're producing something and there's some output, and you do nothing to fix the system or adjust the system or tune the system, right? In decisions in real life, do nothing is almost always an option, right? You don't have to do something. And it's an overlooked option, whereas sometimes doing nothing could be the right answer. Anyway, I'm not saying it's the right answer here. I'm just saying that it's a valid option to consider. The second strategy is to tune, okay? And how do we tune? So if a marble lands like to the right of the target, that means you're shooting too far to the right, so you move the funnel to the left, right? Because if your marble is landing to the right and you move the funnel to the right, it's going to land even more to the right. That's the idea. So if the marble lands to the right, you move the funnel to the left. If you move too much to the left, the next marble may land to the left, so then you move it a little bit to the right. So you keep adjusting to try to hone in onto the target. Okay. And the real life comparison is very similar. You can adjust machinery. Let's say you have a filling machine and it's filling up bags of product and it's putting in 100 grams extra of product in the bags. And you don't want to ship extra product to the customer. So you set it up to try to push out 100 grams less each time because it was pushing out 100 grams extra each time, right? So that's the idea. You tune in the opposite direction to correct for the error in the output. Then the third strategy is what is called reset and tune. So each time the marble falls away from the target, okay, first you try to reset the funnel by looking through it to be on top of the target again. And then because something is happening which is causing your marble to be off target, because you did start in a reset state, right? In the beginning, you did set the funnel up. You tune it like strategy 2. So if the marble landed to the right, you move funnel to the left. If the marble landed to the left, you move funnel to the right. If marble landed above, you move funnel the other way and so on, right? So reset and tune. So it's just like strategy 2, but before the tune, you try to reset by looking at it and reset it on top of the target. And the fourth strategy is you move the funnel by looking through it to whichever point the last marble landed. It's called calibrate to the last output. And this might seem strange in this context. Why would you calibrate it to where the last marble landed? But this does have a real life comparison. There are cases where companies or production systems are calibrating to the last output. You might ask how? How is that possible? If there's no standard, okay, then you look at what you just produced and you make a copy to produce the next item. Then when you produce the next item, the initial item is probably already sold. So the item you just created, you look at that as a copy to create the next, as a model to create the next item, because there's no standard. So this is like producing without having a standard. The other case, this type of strategy might play itself out unconsciously, even if it was not designed to be, is that there's a lot of turnover. So workers leave a lot and new workers come and get trained. So if a worker is doing things a certain way and he's going to leave, the new worker comes, he's getting trained under this worker, the new worker learns this worker's ways, then this worker leaves. This new worker might change up the ways a little bit, but then when the third worker comes, this worker trains the new worker now, and everything this worker added to the process gets passed on to the third worker, and then the third worker passes on their things to the fourth worker, because every worker that's there trains the next batch of workers, and the next batch of workers in the next batch, because there's a lot of turnover. So you could have calibrate to the last output happening in that situation. So these are like kind of like 4 real life type of strategies that we can use, or you can come up with your own strategy and do it. So now pause the video and think which of the strategy would win. So if we had 4 teams, each following one of these strategies. So strategy 1 is lazy boy, strategy 2 is tune, strategy 3 is reset and tune, strategy 4 is calibrate to last output. Which strategy do you think is going to win? In my experience, when I ask people, option B, which is tunes, the second strategy, and option C, which is reset and tune, which is the third strategy, tend to be popular among students. But you don't have to go with the majority or what's popular. You make up your own mind, and then you can unpause the video and see what happens. Okay. So as Deming loved to say, in God we trust, everyone else must bring data. We have to test these 4 strategies to see which one will win. Okay. And now I don't have a funnel and the whole thing set up to show you, but what I can show you is using a simulation which simulates this experiment. And you can, and the actual experiment results support the simulation results. But if you don't trust me, you can buy the equipment and try it yourself. I'm going to show you the simulation results. So here are the pictures of a simulation results from dropping 50 marbles. Okay. The circle or the rectangle is drawn afterwards to capture the entire area over which the marbles are dropped. So the size of the circle or the size of the rectangle suggests, like, the variability in your drops. Okay. And the target, okay, is given by this crosshairs. I don't know if you can see it well, but if you look at rule 1, which is lazy boy, this white crosshair right smack in the center is where the target was. In rule 2, which is tune, this crosshair on the middle left right here, this is where the target was, and the center of the drops was this red circle. You can barely see it here. See, sometimes you can see the red circle if there's not a lot of black points on it. Yeah, actually, actually, I'm not sure what the red circle is, because I thought this was the center of the actual marble drops, and it shows how the center is different from the target. But in rule 4, this does not seem to be the center of a marble drop. It should be somewhere here. So I don't know what the simulator did with the red circles. But we can ignore the red circle. We can kind of guesstimate what the center of the marbles is, right? So we can see that tune, which was rule 2, which is the most popular choice of students, they feel tuning it would get you better results. Here's the target. The marbles are dropping off center, and their standard deviation of the location of the marble drops versus the location of the target is 17.3. Do nothing or lazy boy has a standard deviation of 11.9, and the center of the marble drops is exactly on top of the crosshairs. So on average, we are right, because if the center of our marble drops matches the target, that means we have no bias. On average, we are correct. The tune introduces some bias, and there's more variability. Reset and tune just is awful. Okay, it's all over the place. And calibrate to last output is also awful. It's all over the place. Look at the standard deviations, 58.9, 83.4. They're just terrible. Okay. But surprisingly, rule 1, which is do nothing, wins. Okay. Unfortunately, if you follow the link to the online simulation, the simulation was made with using a software technology called Flash by Adobe, which is no longer supported, is no longer maintained, so the simulation is not working right now, but I'm thinking of creating the simulation myself online, and then I will replace this link when I get time to do that, so you could actually play this game. But for now, you just have to trust this output when I ran the simulation when it was still available, and then hopefully, I can code up the simulation and give it to you to play with it yourself. Okay. So why does lazy boy win? That is what we have to understand. Okay. Now, what's happening here is that you have a funnel. When the marble enters the funnel, obviously the funnel is wider than the marble. If the funnel was not wider than the marble will get stuck. So because the funnel is wider than the marble bounces around on the sides of the funnel and kind of shoots out at a random angle from the output of the funnel. Yeah, a little bit of an angle, because obviously the funnel is not too wide. If the funnel was much wider than the marble, it would bounce around and come out at very different angles. But the funnel is kind of narrow. There's not too much, there's not a lot of movement of the marble laterally bouncing around. There's some movement. It comes at a little bit of an angle. And because it comes at a little bit of an angle, and the distance between the funnel and the paper has to be maintained. You can't move the funnel closer to the paper. That's not allowed in the experiment. So because the distance between the funnel and the paper is constant, and the marble comes out at slightly different random angle each time, it falls at a slightly different place. And then the other factor could be if there's, wind blowing and the wind has a little bit of an effect on a marble or not. I think that's going to be negligible. It's mostly the angle it comes out on, right? And that's what causes this dispersion. Now, Deming is trying to get you to learn that this angle at which the marble comes out in, which is causing this deviation on where the marble lands, is not due to operator error. When the operator puts the marble in at the top, operator can't do anything really to control the angle at which the marble comes out. Maybe if the funnel was really wide, the operator could drop it right in the center of the funnel so it doesn't touch any of the sides and just drops down vertically. But the funnel is not that wider than the marble, so that's kind of very hard to do. That's not feasible that the operator can do that every time. So it's going to bounce around the funnel. So it's chosen to be like that, right? So it's not operator error really. It's the system, it's a feature of the way the system is designed, the feature of the way where the machine is designed, where the machine is going to have that much error. Now, when you have some error in the system or error or variation, this variation in the system, it's hard to call it error because error depends on the specification. We haven't said what the specification is. What's the allowable circle in which the ball has to land. So let's not call it error. Let's just call it variation. So this variation in the system of the funnel and the marble's interaction is inherent in the system. It's not caused by operator error. It's not caused by somebody jumping on the table and moving everything around. It's not caused by an earthquake. It's inherent to the system. So when you have variation that's inherent to the system, messing with the system by tuning, by reset and tune, by calibrating is not going to help because that variation is inherent in the system. Anything you do to the system is only going to increase the variation because you have variation inherent in the system that you can do nothing about. And your actions add more variability to the system. And so which is why rule 2, 3, and 4, all those other strategies that where you do something to the system, they end up in increased variability. Okay. If, for example, there was a problem with the system, if you start off with a funnel which is not on top of the target, remember when we start the experiment, we look through and we always set the funnel properly. If the funnel was not set properly, that would mean there's a system error, then fixing that error would help you. So if your funnel is off target and you drop some marbles, they're all going to fall off target. So if you move it to the center, then tuning will help you because there was an error in the system. But remember, in this experiment, we start with the system set correctly. There's no error in the system. So when there's no error in the system, messing with the system increases variation in the system. Because, so if there's no error in the system, let the natural variation be, don't mess with it. If there is error, then you can correct the error. So what Deming's conclusion was He said there's two types of variation. A natural or normal variation in the system that just depends on your technology choice, the precision of your instruments, right? If you're measuring with a ruler, you can only measure things to certain precision. If you're measuring with, like, I don't know, laser or whatever, maybe you can measure more exactly. So whatever system you have, there's some limits to whatever system you have. It's only accurate to within a certain amount. So there's some normal variation in all physical systems, okay, especially those involving humans too. And that normal variation is going to be there. That's the natural or normal variation. And then there's special cause variation, which is the system is not set up correctly. So if there is special cause variation, you need to go and tune and you need to fix the system. But if there is no special cause variation, do not mess with the system. That's the answer that Deming is giving you, okay? So the conclusion is that if the system does have a problem, you can go fix it. But if there is no problem, just the system has natural variation, there's nothing you can do with the employees, motivate them, incentivize them, nothing you can do will fix it. This is actually a very important general management lessons as well, because so many managers do not understand that management is more than people's management. A lot of people, somehow they get this idea, maybe they feel that organizational behavior or HR is the only type of management there is. I don't know where they get this idea. But some people have this idea, I'm going to hire the right people, I'm going to give them incentives to do the job right, and then as a general manager or CEO, my job is done, I can just sit back and relax, and because I hired the right people and I gave them the incentives to do well, everything will work correctly. Well, that will not happen if the people don't have the power to fix errors in the system, because if the system is designed, or if there's no errors to improve the system, well, let's say the system has too much natural variation. So you hire the people and you give them incentives to fix any problems, if like tune the system up, and the system output is not accurate, is not meeting customers' requirements because the system has too much natural variation. These people are going to try to tune the system and mess up the system even more, and nothing is going to get fixed ever because you haven't figured out, you haven't separated the natural variation from the special cause variation, and you haven't upgraded the system to have lower natural variation. Because, if you look here, what Deming is saying is, if strategy one, rule one, if this is too much variation for you, you can't do any better by just incentivizing people to tune the system. You have to get better technology, just upgrade the whole process, upgrade the whole system. Okay? If your machine has too much variability and it can't meet customer requirements, you have to get a better machine. You can't just tune the machine into getting better results. The machine is just not capable. Right? If the natural variation is too much, that's an issue of process capability. An incapable process will beat good people every time. That's what he means here. A bad system means an incapable system. A system which is incapable of satisfying the customer because the system has too much natural variation. You can hire the right people. You can give them millions of dollars of incentives. They will never get anything right because the system has inherent variability that is too much, and you need to upgrade the whole process, upgrade the whole system. And the idea here is that the lower level employees don't have the power and the ability to do that because they can work within, you don't give your assembly line workers the power to just buy a new factory, set up a new factory, right? They don't have the budget or the power to do that. So they're stuck with what you give them. So which is why, please, as a manager, your job is more than just hiring the right people and giving them the right incentives. That is an important part of management. That is not all of management, okay? So please, HR students, take note, because if you have a system that's not capable, no matter what you do in HR, no matter what you do in organizational behavior, no matter how motivated people you bring, it's not going to fix itself. Okay, so this is the summary of what you're supposed to learn from the funnel experiment. Any difference or deviation from the target, the norm here means the target, okay, what you're trying to achieve, is variation. There will always be variation in physical systems. Okay, common cause, normal, natural variation, they are terms for the same thing, is inherent random variation in a process that cannot be reduced by adjusting or correcting. The only way to fix common cause variation, like not fix, like reduce it, is to go for better technology, more precise technology, which is going to have a capital expenditure cost, going to be more expensive. And so you have to see if it's warranted or not. And then there could be special or assignable cause, sometimes also called abnormal variation, which is caused by some external influence, like defective raw materials, like the machine not being set correctly, the settings are off, like some part of the machine failing, like the machine requiring maintenance, right? An untrained worker, inexperienced worker, these sorts of things. Okay? And these are, you have to take care of it. You can reduce it and take care of it by training the worker, by maintaining the machines properly. Like total preventive maintenance is a way to do that. Total preventive maintenance is the idea that you maintain the machines before they fall apart so that they never have special assignable cause variation due to the machine issues. Right? You replace parts as they wear out, things like that. Okay, so you fix that. Now, this is the big problem that Deming is trying to solve. When you observe the output and you see variation in the output does not, repeat, does not tell you if the variation in the output is because of common cause or special cause. So you're just seeing variation in the output. You don't know if this is special cause variation, is my machine having an issue, or is my worker untrained, or is it just the natural variation in the process? Like the output itself doesn't tell you. The output only shows you the variation. So how do we figure it out? That's the next part of the lecture, and it's going to teach you how you figure that out. Okay. So if there is no special or assignable cause variation present, then do not tamper with the system. Because there's only common cause variation present, tampering will introduce more variation. Okay. If common cause variation is too much to meet customer expectations, then you must get a new technology, more accurate equipment, things like that. Revamp your entire process, start from scratch. Right? Go to step one, go to a whiteboard, clean slate, right? And if there is evidence for special cause, assignable cause variation, then you investigate what's causing it and you eliminate the cause. The cause could be a worn out part in a machine, the cause could be unmaintained machines, cause could be untrained workers, cause could be defective raw materials or components, whatever that cause is, you have to do root cause analysis and kind of fix it. Okay, so now we get to the next part of our lecture. We're going to study the two ideas that are going to help us do this thing on the slide. Identify special cause variation, eliminate it, and also evaluate if common cause variation is too much or not. Like how much is too much? How do I know I need to go for a new process? Whereas how do I know I can stay with this process and it's going to be fine? So this idea of first checking is the common cause variation sufficiently low that this process is going to meet customer requirements or not. That's called process capability. And then figuring out whether special cause variation is creeped into your system or not, that's process control charts. That are the next two things we're going to study. Okay, so hopefully I want you to pause, take a breath, ask yourself, do you understand the basic idea of Deming's funnel experiment? Do you understand variation? Do you understand what is special cause variation? Do you understand what is common cause or normal variation? If you understand these concepts, proceed. If you don't understand these concepts, go back, watch this segment again, maybe think about the slides, ask me, email me if you still don't understand it. Okay, so let's get into process capability. Okay, so process capability is the ability of the process to meet design specifications for a service or product. It's very important to recognize that process capability, to calculate it, you need to know some specifications. And these specifications should not be based on process statistics. They should not be coming from your process. The specifications should be coming from the design team, from the customer. So hopefully the product design team looked at the customer, looked at customer requirements, and translated the customer requirements into a design specification. From those specifications, we get our process specifications. Okay? So we don't just look at our process and say, oh, on average it does this, so this is our spec. No. The spec must come from outside the process, from the voice of the customer, translated into technical specifications. Then once we have those specifications, process capability compares the common cause variation of the process and sees, can our process meet these specifications if there's no special cause present? So usually we're going to have a target value, okay, and it's going to be the midpoint of our tolerance limits and some tolerance or specification limits that come from those design specs. Now, when we think of process variability and the target value, there are two things that can happen, which are shown on the left and the right targets. And then when both those things are fixed, what we get is the center bottom target picture. So in the picture on the left here, it says process average okay, too much variation. If you look at the X marks, which is where we are hitting, they are uniformly distributed all around the target. So we don't have any bias. We're not biased to the right or biased to the left or biased to the top or biased to the bottom. We're all around. So there's no bias in our process, but we are not close to the center. A lot of our X's are all over the, like distant from the center. Okay. So if we take an average of all these X's, we will get the center. So the average, on average, you know, we have equal number of X's to the right and left of the center, equal to the top and bottom. So on average, we are centering it. The center of our X's matches the target closely, but there's too much variation. Our X's are all over the place. Versus you compare to the picture opposite it to the right, where it says process variability okay, process of target, you can see that the X's are clustered together close to each other. So we don't have a lot of variability in our output, but our output has a bias to the top right of the target. The center circle is the target. So we have a top right bias. On average, we end up above and to the right of the target, but we do end up on the same spot or around very close to the same spot each time. If we fix the variability and we fix the bias, we get the picture on the bottom where you can see that you have a closely clustered points, X's. So there's not a lot of variability, and you know, on average, the center of the X's is very close to the target. So we are on the target, so our average is okay and our variability is okay. So to have process capability, we need like the bottom picture where we are centered on the target value or close to centered on target value, and our variability is low, so that our output is going to be, you know, very close to the target, so which is going to be probably within the design specs. This is an illustration of A, the first figure with the green curve where a process is capable, and B, the distribution of output for an incapable process. So the key to notice is our specification limits, which is 20 to 30. Upper spec is 30. It's something to do with time, so we need to get done within 30 minutes. And the lower spec is 20. We are allowed to take up to 20 minutes. That's totally fine. So we need to be somewhere between 20 and 30 minutes. Maybe below 20 minutes, we wouldn't have time to do a good job, so we don't want to take too little time. Maybe something like baking a cake or whatever, right? You need to bake it for 20 to 30 minutes. It could also be how long you do a chemical reaction. If you do it too little time, the reaction is not finished, so the output chemical is not right? Could be anything like that. Okay, so the target value or the nominal value is the midpoint between the tolerances, which is 25. And the green curve shows a distribution like a histogram of our actual output values. And you can see our output values always fall below the specification limits. So that means the variability in our output, there is variability in our output, but it's not large enough to throw us out of spec. Even with the variability, we are between 20 and 30 minutes all the time. Now look at the red curve. In the red curve, if you look, a large part of the red curve is outside the upper spec of 30 minutes. So the process variability is so much and the process is off center. You can see the peak of the distribution. The most common output is not at the nominal value of 25. It's to the right of 25. It's like 27, right? And then we have a lot of variability. So being off peak plus the high variability makes it so that a lot of our output is out of spec. Obviously, not every single output is out of spec. You know, we have a lot of output in spec too, but there's too many units being produced out of spec, which is not Good. So that's an example of a process that's not capable. So to make the red curve process capable, we can move the center value of the process to close to the nominal value of 25. And even if you move it there, we'll still have the curve hanging outside the 30 minutes mark. You'll have to also tighten the curve, which is reduce the common cause variation. We're going to look at two metrics of process capability. The first is called the process capability ratio, CP. C stands for capability, obviously. P stands for process. Okay, and the process capability ratio is the tolerance width, which is the upper spec minus the lower spec. So how wide is our tolerance? Upper spec minus lower spec, divided by 6 times sigma, where sigma is the standard deviation in the process output. Yes, if you go back to this picture, sigma is a measure of how wide this curve is, the green curve or the red curve. Okay, so what we're seeing is that the sigma should be so small that 6 times sigma should be smaller than the tolerance limit, because CP has to be more than 1. CP below 1 indicates process is not capable. Okay, so upper spec minus lower spec divided by 6 times sigma. So how do we get sigma? We set up the process in its ideal state. So we have fresh machines with the lubricated, maintenance taken care of. We check every single part. Everything is fine. Nothing is worn out. They're operating as suggested by the manufacturer of the machines. We have fully trained, experienced workers. We have tested all the raw materials. They're all fine. Temperature, everything is perfect. It's like a laboratory control type of setting. And so when everything is perfect, we run the process and we measure the output and we measure the variation in the output using some exact measurement. And then we can get the standard deviation of the output, and that's sigma. Okay, so in our ideal conditions, what variability is in the output? That's sigma. Okay, the standard deviation. So it's obviously based on some measure. If the volume, if the mass of the final product is important, we're filling product into bags, we can use the mass, measure the mass and get sigma. So if there are multiple design specs, we'll have multiple sigmas and multiple CP measures. One for the size of the product, one for the weight of the product, things like that. Right? But in this class, we're going to assume there's one measure that's important. Maybe it's the weight, maybe it's the volume, maybe it's the size, maybe it's the some other type of output of the product that's important, and we are able to measure the standard deviation in the output, that's sigma, and then we can measure the process capability ratio, CP. Remember, okay, this is a very common mistake students do. They'll look at the process, the past values of the process, and they take like a large value and the small value as their upper spec and lower spec. Upper and lower spec never come from the process. They're not voice of the process. They're not based on output of the process. Specifications are always coming from outside the process, from customer requirements put into the language, into a technical language by engineers or process design people. Okay. The customer could be internal. You could be making a part that's going to be used by another part of your organization. So maybe you produce brakes and then the manufacturing assembly line uses the brakes and they are the customer and they tell you the design specs, right? So the customer, when you say customer in operations, it doesn't always have to be an external customer. It could be an internal customer within the supply chain. The second metric of process capability index is called CPK. The previous one is called process capability ratio. So you're going to remember that ratio is just CP. Ratio is just a simple ratio. Upper spec minus lower spec, the width of the specs limits or the tolerance limits divided by 6 sigma, just a ratio. So that's why it's called ratio. And then the index is a little bit more complicated to calculate. You have to calculate 2 values and take the smaller one. That's what the minimum of means. Minimum of means within the brackets, you're going to get more than one value, in this case 2 values separated by a comma, and you take the lower of the 2 values. So you're going to do 2 calculations, take the lower. That's what the minimum of means. Okay. So what are those 2 values? The first value is we take X bar bar. The X bar bar is the long run average output of the process. If you want to think of it in a picture, go back to this picture. X bar bar is the peak of this distribution. So for the green process, X bar bar will be 25. That's where the peak is. And for this red process, X bar bar will be something like 26.5 or 27. It's more than 25. Okay, that's where the peak is. So that's X bar bar. So the long run average is what's going to be the peak of your distribution, because the variation is usually around the mean. It's above and below the mean. So the center of the distribution is going to be the long run mean. Okay, so that's X bar bar. So where the peak is minus the lower spec. So you calculate the distance between the peak and the lower spec divided by 3 sigma. Okay, that gives you one value. Then the second value, you take upper spec, because upper spec is going to be most likely above the mean, because mean is going to be between the upper and the lower specs, right? So the mean is bigger than the lower spec, but the mean is going to be smaller than the upper spec. So you always take the bigger number minus the lower. So the top part of this calculation should not be negative, right? Usually will not be. If it's negative, then you are like so far away from the center that you are just, it's a lost case. You're terrible. I mean, you still need to change you need to improve. But if you get a negative value, that means you're terrible. In most real cases, you're going to get a positive value, because X bar bar will hopefully be above the lower spec. And X bar bar will hopefully be below the upper spec. So upper spec will be a bigger number minus X bar bar over 3 sigma. Okay. Sigma is the same way as CP is the standard deviation of the output of the process, same sigma here. So you calculate these two numbers. Now, if X bar bar is smack in the center of the upper and lower spec limits, you'll get the same value. Okay. But if X bar bar is closer to one of the lower or the upper spec, then that will get you a smaller value, and you have to go with a smaller value. So if I go back to this picture, okay, let's see if I can write on the screen. In this case, the X bar bar has the same distance from the upper spec 5 as it has from the lower spec 5. So your CPK will become minimum of 5 over 3 sigma, right? Because X bar bar minus lower spec is 5, comma 5 over 3 sigma. Why another 5? Because upper spec minus X bar bar is also 5. Okay, so it'll be the same number. You just pick whichever one. The minimum is of 2. Minimum of 2 and 2 is just 2, right? Minimum of 3 and 3 is just 3. So minimum of 2 identical numbers is just one of the numbers, so that you can pick whichever one. That's your answer, right? So answer will be 5 over 3 sigma. Okay. Now let's change my pen's color. I should have used red for the other one. Okay, let me just use different shade of red here. So for this one, this is gonna be your X bar bar, and let's say this is equal to 27. Then your CPK will be the minimum of, okay, lower spec, X bar bar minus lower spec. So this distance here, 27 minus 20 gives you 7. So 7 over 3 sigma. And then the next will be upper spec minus X bar bar. So this distance right here, that's going to be 3. If this is 27, 30 minus 27 is 3. 3 over 3 sigma. And now you can see that the 3 over 3 sigma is going to be a smaller number than 7 over 6 sigma. So your CPK will be 3 over 3 sigma. So notice that in CPK, when you're off center, you look at the worst case, because this side where you're close to the upper spec is where you're going to have more defects. All of these are defects, right? Whenever your red line is here above the upper spec, this is all defects. So you're going to have more defects on the side where you're closer to the spec, right? So that's why CPK takes into account an off-centered process. So CPK is a very nice index, a measure of process capability, because you may have a small variability. Your process may be very tight, but if it's off-centered and close to one of the specs, you're going to have errors on that side. So it's going to look at the side you're closer to the spec, because you're more likely to exceed the spec on that side. Okay. Whereas CP, okay, let's say our standard deviation, whatever standard deviation, CP is going to be for this process 30 minus 20 or 10 over 6 sigma, which is 5 over 3 sigma. So notice when the process is centered, CP equals CPK, right? CP, which doesn't concern with X bar bar, is not concerned with centering. So CP is 5 over 3 sigma and CPK is 5 over 3 sigma. But when you're off center, okay, in this case, CP is still going to be 10 over 6 sigma, which is 5 over 3 sigma, but CPK is 3 over 3 sigma. So notice that when you're off center, CP does not detect it. CP is only comparing the variability in the process with the allowable width, okay? Whereas CPK detects if you're off center or not and adjusts for that because CP might say everything is fine, but you may be getting errors because you're too close to one of the limits, and CPK will detect that. So CPK is nice. Another way to explain that is, let's see if I can draw a diagram here. Okay, let's say you have a garage and you have to park a car. This is your garage or parking space. Okay, or a parking space. And this is your car. Okay. Now notice that the width of the car, let's call it W1, is smaller than the width of the garage, W2. Whenever the car is less wide than the garage, you're able to park it, right? So that's what CP is testing. CP is testing, is it possible to park the car? The car represents your process, so the width of the car is the variability in your process output. The garage represents your specifications. So as long as the process width is less than the spec limit, you can park the process, is going to work. Is it possible to park the car? Okay. Now, CP would still be fine if my car, if I didn't line up my car, if the same car, same width, was right here. Okay, I have the same width, W1, same width. But this is the wall of the garage. If I back up here, I'm going to hit the wall. I'm not going to be able to park it because I'm not centered. So CP doesn't care about that. CP doesn't say whether the car is centered or not. And if you're going to hit the wall of the garage, you're going to go in the garage. It doesn't care about that. It just says the width of the car is smaller than the width of the garage, so it's possible to park it. Whether you destroy the wall and mess up your car or not is not CP's problem. CP is just saying it's possible. Okay. CPK on the other hand, worries about the center. It's going to look at the center of the car here, and it's going to compare it with the wall, this wall and this wall. It's going to say you're closer to this wall, so it's going to take that and say, oh no, my width is not small enough to park if I am close to this wall, so this will not work. This will be detected by CPK. So it's not going to work. You know, your center is too close to the wall. You need to move your center towards the center here. You need to move this center in here, move the car somewhere here, and then you can park. You can't park here because CPK detects the off-centering. Okay, so you can think of it like this. CPK is going to detect if your car is lined up properly to go in the garage or not, the center of the car versus the center of the garage or the walls of the garage. CP doesn't care about that. It just cares about the width of the two. CPK also cares about the width, but it also says that this width is going to be compared with the closest wall, not with the entire width, because if you're close to one wall, then that's what matters. Okay, so hopefully that made sense. Okay, let's continue. Let's look at what values of CP and CPK are acceptable. Okay, a CP of 1.0 or a CPK of 1.0, both of them indicate what we call a 3 sigma level of quality. So this is called 3 sigma quality level. Okay. What that means is that the upper spec minus lower spec, so the width of the specs over 6 sigma equals 1. So because your process width is 6 sigma, your process, if these are the spec limits, you know, upper spec, that's US, lower spec, your process is just as wide as the spec limits. So your process is so wide, it fills up the specs, but it's not wider than the specs. Okay. So if why? Because Because on average in the normal distribution, you're going to deviate from the center about 3 sigma to the right and 3 sigma to the left. In a normal distribution, you're usually 99.7% of values are within 3 sigma of the center. So if your process is 6 sigma wide, if the 6 sigma of your process is the same width as the specs, then 99.7% of the time or something like that, some high value like that, you're going to be within the specs if you're centered properly. Okay, so that's called 3 sigma quality. We talk about sigma quality levels in terms of defects per million opportunities. If you make 1,000,000 units, how many will be defective? If your process is exactly centered, 1,350 out of 1,000,000 units would be defective if you have 3 sigma quality. But processes tend to drift. They're not always centered. Okay, if the process drifts by 1 standard deviation, you're going to get a lot of defects. Okay, so I just made a small correction to the slide. This thing was set to white font, so it was not displayed. So if it drifts by 1.5 sigma, that's a pretty big drift. Even if you look at, if you calculate, if it was to drift by 1 sigma, you would get thousands and thousands of defects. So 3 sigma level of quality is not a very high level. You usually want to be a little bit higher than that, or considerably higher than that. Okay, so that's why it says barely acceptable. A 4 sigma level of quality means that CPK would be more than 1. So upper spec minus lower spec would be more than 6 sigma. So you get 1.44. What it actually means is that upper spec, lower spec, if this is the center, this width here is 4 sigma, and this width here is 4 sigma, and your process is going to be like this. So it's not touching the sides. There's a 1 sigma gap here. There's sigma here, a sigma worth of gap here, and a sigma worth of gap here, because this is 3 sigma and this is 3 sigma. Okay, so 6 sigma width is inside your 2 specs, and you have 1 sigma extra on each side, which is why this part here is called 4 sigma. So that's 4 sigma level of quality. And now if your process is centered, look at that. Only 32 defects per million. So you make 1,000,000 units, only 32 defective. You can calculate as a percentage, 32 over 1,000,000. Okay, that's gonna be in terms, and multiply by 100 to convert to percentage. That's gonna be 0.0032% defect rate. A very tiny defect rate. Okay, and even if you drift a lot, you still got 10 times less errors than a 3 sigma quality. So it's an order of magnitude improvement. If you're centered, you're very, very good. If you're off centered, still you're doing much better than 3 sigma quality. And now look at 6 sigma quality. This is amazing, right? CPK value of 2. So your upper spec and lower spec over 6 sigma, you get 2. So this width here is 12 sigma. Okay, if this is the center, your process is here. 3 sigma, 3 sigma, there's 3 sigma extra here, and there's 3 sigma extra here. So even if you deviate outside plus minus 3 sigma of your process center, you're still very far from the upper and lower specs. So with a CP and CPK value of 2, which is called 6 sigma quality, which is where the term Lean Six Sigma comes from. 6 sigma as a quality management tool, it aims for 6 sigma level of quality. That's where the term 6 sigma comes from. So if you have 6 sigma level of quality, your defects per million opportunities is going to be basically 0.00 something or 0.0 something. Okay, and even if you drift by a lot, look at that, you drift by 1.5 standard deviations, your defects are still so low. Very highly capable process, right? Now, this is not always possible to get to 6 sigma quality, but you aim for that. If you end up at 5 sigma, 4.5 sigma, whatever, that might still be acceptable, but this is really good quality level. Okay, so why does it matter when being good is not good? Why we're going to compare 99% good with the Six Sigma level. Okay, so about 4 Sigma level versus 6 Sigma level. Okay, a lot of people say 99% good, 3, 4 Sigma level is pretty good. But if you did that, you would have 20,000 lost articles of mail per hour in the US, whereas 6 Sigma level, only 7 articles of mail are getting lost per hour. Unsafe drinking water for almost 15 minutes each day. If you look at all the water output and you only 99% quality, that means 1% of the time there's going to be something bad. And in 6 Sigma level, 1 unsafe minute every 7 months. So much more acceptable, palatable when health is concerned to be 6 Sigma level than something lower. With 99% good, 5,000 incorrect surgical operations per week. 6 Sigma level, only 1.7 incorrect operations per week in the whole of the US. 2 incorrect landings at most major airports per day at 99%. 6 Sigma level, 1 incorrect landing every 5 years. 200,000 wrong drug prescriptions per year versus 68 wrong drug prescriptions per year in 6 Sigma level. No electricity for almost 7 hours each month if electricity supply is 99%, but only 1 hour without electricity every 34 years if you're a 6 Sigma reliability in electricity supply. So you can see easily that in systems that are important to sustain life, in key systems, we want 6 Sigma quality. And the last one, just additional stats there. You would have 50 newborn babies dropped per day. If you're looking at, handling of newborn babies, the quality level there. If you're in 3 and 4 Sigma, but if you go to 6 Sigma, obviously, you remove a lot of that. So the whole point of this slide is to tell you that 6 Sigma is not some unrealistic level of quality. In most systems that affect safety, that support life, you want even higher level than 6 Sigma, or at least 6 Sigma level of quality. There's another great quote by Debbings: learning is not compulsory. Learning is what you need to do to get a 6 Sigma level of quality, because you can just randomly throw around a process and expect things to work at 6 Sigma level of quality. You have to learn and improve your quality. And so all these quality management systems incorporate an aspect of learning in them. And so Deming said, if you don't want to learn, it's not compulsory, but neither is survival. So you may not survive as a company. Okay, now we're going to go into statistical process controls. So remember, in terms of variation, we said common cause and special cause variation. When there's no special cause variation, we said everything very nicely. We can measure the process standard deviation and calculate the capability of the process. Now, if the process is capable, now when we run the process, I said processes can drift over time, things can happen over time. Now we're going to control the process. There's no point in trying to control an incapable process, because an incapable process, is gonna generate defective output by definition if the process is not capable to generate the right output. So first you have to get the process capable, at least at the CP level, which assumes a centered process. Then maybe statistical process control will detect off-centering, and at least CP level you have to be capable, even if CPK is a little bit off because you're not off-center, and then process control will detect when it's off-center and help you bring it back. And so you have to have a capable process before you go into statistical process control, which is why that's how it should be taught. Unfortunately, in many courses and textbooks, they go straight into process control, and then process capability is given like a footnote or just a page at the end of the chapter, which is completely backwards, because why would you want to control an incapable process? It doesn't make sense. So you have to first identify if the process is capable or not. If it's capable, now you want to control it, you want to make sure it stays on track and keeps producing the right output, so that over time, as things can change, we don't get to a state where we're producing defective output. So the idea of control only applies when you have a capable process in the first place. There's really no point trying to control an incapable process. You have to make it capable first, make changes to it, to equipment, your process, your training. All those things have to be changed until the process is capable. And then once it's capable, then we'll do statistical process control.